So thank you very much, Matthias, for coming. And I'm sure the seminar will be very interesting to our students. Thank you.
Okay, hello and welcome. Thanks for the kind introduction. So as said, my name is Matthias Magdowski from Magdeburg. Everything starting with M and A and quite easy to remember. So it's a pleasure for me to be here. It was a quite difficult journey coming from Magdeburg. If you don't know where Magdeburg is, I will show you in a couple of slides. So I came via plane to Lisbon and then arrived here on a Flixbus very late at night or very early in the morning the day before. But now I'm here and I would like to tell something and introduce you to the modeling of DC motors, so direct current motors. I also brought in a big suitcase a small motor. So this is the one that I will be using for some experiments. I have also set up some quite fancy equipment here. So I also have a document camera so that you should be able to somehow see the experiments that I'm doing here on my table. Okay, so before we start, and because I have some quizzes also in between, and I want this to be a little interactive, and there are more students, so come in. Please join us. So I have some introductory questions for you. I mean, everyone is talking about artificial intelligence these days, so I have a quick icebreaker question. I would appreciate if you would take your cell phone, scan this QR code. Hello, come in. You should come to some web page where there's a survey with 9 options. So on a scale of artificial intelligence, how are you feeling today? And we have options from, this is a mechanical Turk that was something like a fake chess robot. So people were thinking this is a robot that was playing chess, but there was just a person hiding in there that would really play chess. We have the famous Texas Instruments calculator. We have the over-engineered coffee machine from some movie that I don't recall at this moment. Then we have, does recall anyone what this is? Or does anyone know from which movie this is? No. Yeah, this is HAL 9000 from the movie 2001: A Space Odyssey from Stanley Kubrick. This is, of course, R2-D2 from Star Wars. This is Data from Star Trek. This is a Borg, also from Star Trek. Next Generation. This is Neo from the Matrix movie. And this is Marvin, the paranoid android from A Hitchhiker's Guide to the Galaxy. And so I don't see. Have you casted your vote already? So we can, and hopefully this works. Have a look at the results here. And why do I don't see results yet? Oh, interesting. I see. Why is it saying 0 answers and showing me some results? So I will just reload. The QR code once again? Sure. Okay. So hopefully now it works with the results. And I don't know why it's not showing anything. Even not in full screen mode. Does it work for someone? Yeah, it works for you, but does it not work for me? So you could vote. Okay, I get some help. So okay. I think I still have the wrong QR code there. So the one that has won is the number 9, Marvin, and on the second place we have number 3 and number 7, which is the over-sophisticated coffee machine and the Borg. Okay, thank you, excellent. Thanks for your support. Okay, so quite a good choice, I would guess. Okay, so then some words about myself. So I was born in 1984, also like in a movie from Stanley Kubrick. You can calculate yourself how old I am. I live in Magdeburg. I will show you in a second where this is. In Germany, I am married. I also have 2 wonderful children. And my son is already taller than me. And I have a background in electrical engineering, so I'm an engineer by heart. I studied between 2003 and 2008, also in Magdeburg. And since then, I'm working there as a scientific co-worker at some chair for electromagnetic compatibility. Do you know what electromagnetic compatibility is? Have you heard of this? So we are mainly the reason why you are not allowed to use your cell phone, or why you are asked to switch off your cell phone in an airplane, because this is my old phone, my dumb phone. Of course, I also have a smartphone, yeah, if you remember these older phones, they would nicely interfere, for example, with speakers or with the radio receiver. So if you are sitting in front of a radio, if you would get a call or call someone in the speakers, or also of a computer, which is beep, 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 some very characteristic noise. And so the cell phone, when it's operating, sends some electromagnetic waves, and these electromagnetic waves, for example, interfere with the radio receiver or with the speakers, and they could also interfere with the cabling in the airplane or in the car. Yeah? And that's why it's sometimes better to switch this off. So this is what electromagnetic compatibility is. And I also did my PhD in this topic. You can read the title there. And since 10 years or so, I'm doing stuff like this. Being active as a flying faculty lecturer, we have had the long-standing cooperation with the Russian university. This, of course, does not work anymore. And since then, I've been to France several times, where I've also met some colleagues from Badajoz. And so they invited me here, more or less. And our university is also part of this EU Green network. I don't know if you've heard of this. So there's this university alliance of 9 European universities. One of them is in Magdeburg, one of them is in Badajoz. And yeah, because of this, I'm also kind of here. This is our building in Magdeburg. So I work for a faculty of electrical engineering and information technology. Some of our labs and also my office would be in this building. And our university is also quite close to the city center. It has about 15,000 students in total and 9 faculties. So we have also mathematics and natural sciences, computer science. Then we have the engineering faculties for electrical engineering, information technology, mechanical engineering and process engineering. We have economics, we have a human sciences department and a medical department. And we also have a university clinic like you have here or university hospital. This is some view of our city. We have a large cathedral and many other churches. We don't really have an old town, because Magdeburg was heavily destroyed in the Second World War, unfortunately, and it has been destroyed in some wars in the past. Yeah, but it always has been nicely rebuilt, I would say. And luckily, some of the old churches and the old city center somehow survived. And we also have a river. It's called Elbe, and I would say it's as wide as your river, Guadiana, that you have in Badajoz, but we have more water. We have less flowers and plants on the surface of the river. Yeah, but it's also quite nice to walk there in the summer. It's not as hot as in Badajoz. So we also sometimes have 30 and 35 degrees. Very seldomly, we maybe also have something like 40, but then it's just for one day and maybe for 1 week in a year that we have these high temperatures. And this is where Magdeburg is located. So we are somewhere in this triangle, let's see, between Berlin, Hanover, and Dresden. And yeah, in the central eastern part of Germany. And like Badajoz, we don't really have an airport. We have something like an airport, but there are no flights going from there because there is no real terminal or something like this. So usually you would fly to Berlin or maybe to Hanover or maybe to Leipzig or maybe to Frankfurt and then come by train. And we have many frequent, quite nice high-speed train connections in Germany. We also have lots of delays, unfortunately, but yeah, it's quite okay. And you could also go by Flixbus, for example. Similar system in Germany. So then maybe something about the name patron of our university, Otto von Guericke. So he lived in 1600 something. He was a mayor of the city and kind of a politician, but he was also a scientist and an engineer. And he was doing the new sciences, as it was called at this time. He was doing physics and he was experimenting with air pressure and with the force of the air pressure. And so he did a very famous and well-known experiment. I don't know if you have heard of this, with the Magdeburg hemispheres. So he took two very large hemispheres, about 60 centimeter in diameter, put them together just with a seal between them. And he had a valve, and he also kind of invented the air pump, and then he pumped the air out of these hemispheres, so that in between these hemispheres there was more or less nothing, just vacuum or just very low air pressure. And so these hemispheres were pushed together by the force of the external air, and this air pressure you usually do not feel because we are used to it. And so they are, a physicist would say, they are not pulled together by the vacuum, they are pushed together by the external force or by the force of the external air. And to show and to demonstrate how powerful and strong this force is, he did this experiment that you can see a bit here on the picture. And we also repeat these experiments from time to time when the university has some anniversary. So I think 2 years ago, our university, which is quite young, turned 30. And for the 30th anniversary of the university, we repeated this experiment. So 8 horses on one side and 8 horses on the other side. So 16 horses in total. 8 horses are trying to pull in this direction. The other 8 horses trying to pull in that direction. And with these hemispheres in the center. And usually, the 8 horses or the 16 horses are not able to pull the spheres apart because the external force is so strong. And then usually a small child comes after the horses have tried and opens up the valve, and then the air would flow back into the hemispheres and they would just fall apart. So very nice. So I think he was also a good science communicator, let's say. Doing citizen science or demonstrating science experiments to the public. He also, I think I don't have a picture of this, he also kind of, have you heard of electrostatic discharge or ESD, which is dangerous for sensitive electronic components? If you walk on a carpet, you get charged up and you touch something and then there's a small spark. And I mean, it's not dangerous for you, but it might be dangerous if you discharge yourself, let's say, in the USB connector of your computer or into some. And he also had a large sphere of sulfur that could be rotated, and due to triboelectricity, you could also separate charges there and then generate these discharges. So he was also kind of experimenting with electricity. But the most famous experiment is the one with the horses and with the hemispheres. If you have jeans trousers from Levi Strauss, same experiment, different force. He kind of has borrowed or maybe has stolen this idea from us. One horse on one side, one horse on the other side, and then the horses are not able to pull the jeans pants apart because they're also that strong. And then finally there's some interesting connection of Otto von Guericke with the French language. So he was a German guy, and originally he was spelled like this. Gericke. Otto von Gericke, or Otto Gericke. And then he married a second wife, and he was ennobled. He was becoming a noble person. And the language at this time of the noble people was French. And I don't know how well you know French. I have not really learned French in school. I've learned Russian. But in French, you would then pronounce this Géric and not Gericke. And so they did a cheap trick. They introduced this U in the name, and because of the U, then still in the French language, you would say Géric and not Géric. And that's why he's now spelled with the U, which is silent. So it's just Otto von is this noble title, Otto von Gericke. Okay, so then some organizational matters. If you want to have the slides of this presentation, for sure, I will later on send them to Maribel and maybe to Raquel, and they can share them with you. You can also send me an email. I'm easy to Google, and I will be also happy to send them to you. I'm trying a recording with this camera. You never know if it will work. Let's see if it works in the background. Looking good. I would like to do a live stream, but this somehow did not work. But anyhow, and if you have questions in between, feel free to ask these questions. And yeah, we will maybe come back to the question part later. Yeah, but as said, feel free to ask questions. Okay, so then let's really somehow start with the topic of DC motor modeling. So some introduction and some motivation. And the first question is, what does an electric motor do? Can anyone in one or two sentences explain what is the purpose of an electric motor? And it's also a good practice for you to, or a good exercise for you to practice English, which is also, I think, one important idea of these flying faculty exchange programs. So who has an idea what does a motor do? You have some? Don't be shy. Okay, there's one idea.
Convert the electrical energy into mechanical energy.
Exactly. So we have a system like our nice motor here, and we have cables. And so on the one side, we feed electrical power, and then we want to have mechanical power. Right, so that's the idea. Convert electrical power into mechanical power, electrical power into mechanical power. So there are other motors that do kind of mechanical or chemical conversion, yeah, but we don't, if you want to know about this, study process engineering, study chemical and energy engineering, we will not deal with this here. Okay, so electrical power, mechanical power. Next question is, how can we calculate electrical power?
Can you repeat the question, please?
How can we calculate this electrical power? So how can we define electrical power? From which other quantities could we calculate electrical power? It's a kind of a very basic question. So
Horsepower.
say again?
Horsepower.
Yeah, so okay, horsepower would be a unit, or watt would be a unit, or joule per second would be a unit, Newton meter per second would be a unit of power. But how can we calculate power from electrical quantities?
Maybe Ohm's law.
Now, Ohm's law, we will come back to Ohm's law later, does something with calculating the ratio between current and voltage, which stays constant at the resistor. But come in. Hello, come in. Yeah, any other ideas how to calculate electrical power? Yeah, so it has to do something with voltage and current, but we need to multiply them. So usually in Germany we use U for the voltage. It's the same here. Okay, because most other people in the world would use the V, but for voltage, but I don't really like it because then you have to be very careful what is the V for the voltage and what is the V for the volt, for the unit. Okay, so voltage times current gives us electrical power, and voltage we do measure in volt, and current is measured in ampere. Okay, and yeah, we will come back to resistance later. Okay, so this gives us electrical power. So now the question is, how can we define the mechanical power? Who has some knowledge in physics or in mechanical engineering? How can we calculate, or what could mechanical power depend on? So, of course, it's yeah. Or if you think not of a motor but of any other mechanical power, how would you calculate any other mechanical power or mechanical work, mechanical energy? Because power at the end is energy divided by time, or work divided by time. So how could we calculate mechanical energy or mechanical work? And maybe don't think about the motor, but think about other stuff. So so if I have my heavy suitcase here that I brought to bring my experiments to Badajoz, so if I have this here and I'm lifting it up, so how could I calculate the work, the energy that is necessary to lift it up?
Mass by acceleration.
Yeah, it's so mass by acceleration gives us the force, because the more mass I lift up, or I need to lift up, and the more acceleration it's pulling downwards. Yeah? If I would go with this to the moon, where we have much less gravity and much less acceleration, it would be easier for me to lift it up, but unfortunately we are living on Earth, so we have more gravity. So mass times acceleration gives the force. And force times distance gives the work, because if I lift it up just a tiny bit, I don't need to do that much work, but I need to lift it up more and more and more. Yeah? So the more work I need to do. And then this work, which is force times distance divided by time, this gives power. So if I lift it up very, 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 very slowly, then I need to have small power only. And if I need to lift it up very quickly, I need to have more power. Okay. So then somehow coming back to the motor, how could I calculate the mechanical power that this wheel could deliver? So what would be the force, let's say, for some rotational movement?
How to say in English?
Yeah, the problem is the English word problem. Yeah, it's something like momentum. I would call it torque. Yeah, and the torque is measured in Newton meter. And then we would need to have instead of distance, we would need to have a rotational angle, or that many revolutions. And if we divide it per time, we have revolutions per second, or we have some angular speed, some angular velocity. So if we have more torque and more speed, we get higher power, right? Okay, so the mechanical power is just like this. So the torque measured in Newton meter multiplied with the angular speed in 1/2. Okay. So then, what else do you know about current and voltage? And someone already mentioned Ohm's law. So voltage is resistance times current. Or if we would rearrange this equation, then resistance would be voltage divided by current, and this R is called the resistance, is measured in ohm. And yeah, inside this motor, as an electrical engineer that does not really deals with motors, I don't really care what is inside here, right? Just feed current and voltage. And then we get some mechanical power, but of course there will be some coils in there creating some magnetic field, and the magnetic field makes some forces to rotate the rotor inside this motor. And the coil is made out of a wire, and the wire has resistance. So probably we later on need this resistance of the wire to somehow model the motor. Yeah, and the other thing is, what is the other electric effect of a coil? Which quantity do you need to describe the behavior of a coil? Yeah, maybe, but okay, if we have sinusoidal excitation, if we have AC currents and voltages, then we would care about the frequency. But as said, this is a DC motor, so we don't really have frequency in this case. But the behavior would for sure depend on frequency, or it would somehow depend on time, or it would depend on the transients, how fast things change over time. But if you have a coil, if you have, what quantity do you need to describe the coil? Or, I don't know, the transformers that we have on the shelf there. The inductance, exactly. Or the coil forms an inductor, the inductor has some inductance. And what is the relationship between current and voltage at some inductor? So for some resistance, it's this relationship that if we have a current, we get a voltage. And the more current we have, the more voltage we get. So does anyone know a corresponding formula for some inductance? What happens, when do we get a voltage at some inductance or at some inductor?
When current changes.
When the current changes, exactly. Yeah, so we can have a very high current. If the current stays constant, there will be no voltage induced. But as soon as you change the current, or if you have an AC current that changes all the time, then the higher the frequency, the higher will be the voltage that will be induced. Okay, and so this is called Faraday's law, which is somehow combined with Lenz's law or law of induction, Faraday's law of induction. And you can see here that if we change the current over time, if we have a time derivative of the current multiplied with this inductance, then we get a voltage. And yeah, so there is some, it's pretty small, but I can try to enlarge it a bit if my computer allows me. Yeah, so if we have some changing magnetic flux, then there is some induced electromagnetic counterforce that hinders the current change. So at some inductance, the current always wants to remain constant, let's say, for a smaller period of time. Because if you want to change the current, you need to apply a voltage. Or if the current changes, some voltage is induced. Okay, so this should be enough as a reminder of basic electric formulas. We will see them now later on in modeling a motor. And so once again, this is the motor. Do you have an idea what could be the purpose of this motor? So you can see that there's a logo of a very famous German car brand that has its headquarters not far away from Magdeburg in a city or in a town called Wolfsburg. It's Volkswagen. I think the Spanish equivalent is Seat. So you would probably also find something like this in a Seat car. Do you have an idea for what this is used in a usual car? Yeah, for the windows at the doors. I mean, when I was young, I can remember, maybe it's still somehow popular, that you had something to wind up the window up and down, but in modern cars, of course, you just have a switch and you push a button and then the windows go up or the windows go down. And this is such a motor that would lift and lower the window in the car. And yeah, as usual, it's a motor that would operate on 12 volts, like the usual low voltage operating voltage in the car. And now the question is how to model such a motor. And what we need to do is we need to take into account the electrical behavior. So what happens, let's say, from this terminal to this terminal, and then we have this coil, and the coil somehow produces by the current some torque, and the torque then rotates the mechanical part. And if the mechanical part is rotating, then there is some electromotive force that depends on the speed. So the more revolutions you have per second or per minute, the higher is this back EMF, and this also acts back on the electrical behavior. So if we want to model the motor, we need to model the electrical part and the mechanical part, and they are somehow coupled to each other, right? Because current produces torque and speed produces this back electromotive force. Okay, and so then the electric behavior more or less is, okay, we have the voltage of the source that we apply to these terminals. And then as said, we have a winding, and the winding has a resistance. So here, this is Ohm's law built in there. And then the winding or the coil has some inductance. So we have this law of induction inside this equation. And then we have this back electromotive force. And I mean, this is at the end just a Kirchhoff's voltage law. So it's a series connection of all these elements. And this back electromotive force or counter force depends on some constant at the end, some machine constant that is fixed for a certain type of machine, and then this angular speed, which is this omega. And flux in the motor. But at the end, I mean, we just say this is some constant. We don't care about the details there. Okay, so then we can look at the mechanical behavior of the motor. And there, the current multiplied with the same constant creates some torque of the motor. And then this torque goes into friction. Of course, this is not a perfect motor, so there will be friction inside this motor. Then, of course, the motor, this part not that much, but especially the rotor inside there has some inertia. So I also need some time to spin it up, right? So this is this J. This is the mechanical inertia of the motor. And then we might also have some mechanical load, whatever I attach here, the weight, the mass of the window that I'm pushing up and down in the car. Okay, so, but at the end, the interesting thing is, if you look at this, depending on what we do with the friction, but if we compare it with the equation, that we had before, right here we also have something is the sum of something and so on. This equation here looks quite similar. So it's also the mechanical torque that is produced by the motor is a sum of friction, inertia, and some load force. So it's the same kind of, let's say, Kirchhoff's voltage law. Yeah, when we also have some time derivative in there, like for the inductance, and we also, depending on how we model friction, we might also have something like some mechanical resistance times the angular speed. And yeah, so we could think about different types of friction, and there might be friction inside the motor that is independent of speed and velocity, and we would call this sliding friction. And this is a bit difficult to model at the end because you need to have this jump in between, right? If you rotate the motor in one direction, let's say if we rotate the motor like this way, the friction will be in this direction. If we rotate the motor on the other way around, the friction will be in this direction. The friction will not always be in the same direction. Then there is so-called viscous friction or viscose friction, which is directly proportional to the velocity. And this would remember you of which element that we just talked before? Which electrical element? Resistance. Because for resistance, this would be current, this would be voltage, and we would have the same behavior. So if we put a resistor inside the mechanical part of the equivalent circuit of our motor, this would do something like this viscous friction. And then if you use the motor to have a fan or to have a water pump, something like this, you might have something which is called fluid friction, where the torque of the friction depends on the velocity to the power of 2, or on the angular speed to the power of 2. But once again, it's not really a direct power of 2 function. If you have the speed in the opposite direction, also the power or the torque needs to go in the opposite direction. Okay, and we could just sum this up and have some friction constants, but at the end we would, yeah, it's just at the end something in Newton meter divided by the angular speed. Okay, so as we are all studying electrical engineering and as we would like to become electrical engineers, even me, I'm sometimes trying hard to become a better electrical engineer. So we would like to think about this problem in terms of an electric equivalent circuit, because we are used and we have learned how to calculate such circuits, right? And because we can later put them into a circuit simulator like LT-SPICE, or you are using this Plex or PSIM or whatnot. So on Friday we will have some introductory lecture on LT-SPICE. And so the electrical part, as said, is just we have a source that we can connect to the motor. So the source that I will be using later on is a DC power supply that I have here, right? So this will be the source here. And then inside the motor, as we discussed, we have the coil, we have these windings, this has a resistance, this has some inductance, and then we have a source that gives us this counter electromotive force that depends on the speed. And have you seen this symbol before? This should just be some controlled source. So this is a usual source, and this is a source that would be controlled by the speed of the motor in the mechanical part, right? And so from this equation, our counter electromotive force is this machine constant times the angular speed. We transform this to this equation where we say, okay, this at the end is just the voltage, because it's already a voltage here. And the mechanical speed we will also just convert to some electrical current. And then if this is the voltage and if this is the current, what does this need to be inside the equation? Inside this equation, if this is voltage and this is current, then this quantity should be a resistance, right? And so that's why we say it's a trans resistance, and inside this LT-SPICE or inside circuit simulators, this constant is called K, and that's why I've just called it K here. It's a K factor for the electromotive force. Okay, so not that, would you agree, not that complicated circuit to model the electrical behavior of the motor. We have some resistance, we have some inductance, and we have some additional source there. Okay, so now we can look at the mechanical part and try to put this mechanical part, mechanical equation into some corresponding circuit. And then, oh, it's looking pretty similar because we have a resistance that deals or that models the friction, or at least this viscous friction. Then we have some inductance that takes care of the mechanical inertia of the motor. Then we have some torque that is produced by the motor. And this is once again this controlled source that depends on the electrical current on the electrical side. And then we might have some mechanical load. And this I just once again modeled by some voltage source. And so what we do is we transform this mechanical equation also just into an electrical equation. So the torque will convert into a voltage. The angular speed, as we've just discussed, converts into a current. And then the mechanical inertia is once again some inductance, because the mechanical inertia does the same thing as an electrical inductance. If the motor is stopped, it will be difficult to start it rotating. And once it's rotating, it will be difficult to stop it, because this is the behavior what inertia does. Okay, so the nice thing is, okay, for the mechanical behavior of the motor, we can also have an electrical equivalent circuit. That's maybe the main idea of my talk. Let's say that's the main idea, that we can also put the mechanical behavior into an electric circuit simulator. Okay, so this is just a summary of all the quantities that we have there. I think I've explained this already. And so also this physical formula that the torque depends on the motor speed, we transform into one of these controlled sources, that we have the motor current on the electrical side, and on the mechanical side this will create a torque that we now model as a voltage. So once again we have voltage is something times current, so this something once again is a resistance, exactly. Okay, and it's not real resistance, it's like a trans resistance. It's some factor that in there that converts a current in one circuit to a voltage in another circuit. Okay, so in summary, we have these parameters in the mechanical part. We need to have the resistance of the motor, the inductance of the motor, and this constant for the electromotive counterforce. And on the mechanical part, we have another three. We have the mechanical resistance, which takes care of the viscous friction. We have the mechanical inductance that takes care of the inertia. And we have, once again, this K factor that converts current into torque. And these two K factors at the end are the same. So we have five parameters that we somehow need to determine. Right? And I mean, yeah, so at the end, there's this nice saying of Edward Pelham-Box. I don't know if you have heard about this. Famous saying, all models are wrong, but some are useful. Yeah? And so once again, we are trying to model this motor. The model will not be a perfect replication of reality, but for certain applications, this model will be useful. That's the idea. And for the simple model that we are developing, we need to have these 6 or 5 factors, let's say. And so now the next thing, the next section is about measurements, what we could do, what we could measure to determine these parameters, right? Okay, so what features of the motor could be measured? And at first, and I will give this question to you in a second. So, yeah, first thing is we can have a look at this multimeter. Well, no, an introduction of the measurement devices that I have. So I have a multimeter you all know this, right? You have used this before in some labs. Okay. Then I have my power supply here, which is a quite nice power supply because it's not that big, right? If I try to show this with my camera quickly, I mean it's this one that is here on the table, so you can see it's not that large. It somehow fits into my suitcase, and I think it can go up to 30 volts and 5 amperes of current or something like this, which is sufficient to power this motor here. So then we want to measure current, and measuring current is always a bit difficult because usually you need to open up the circuit, put your meter in between and close the circuit once again. So I want to have something that I can use to measure currents without opening up the circuit, so I have a current clamp. This is from a French company called Chauvin-Arnoux, if I pronounce this correctly, and there's a battery in there because there is some kind of Hall sensor that measures if you have a current going through a cable, you will have a magnetic field around the cable, and so what this current probe does is measuring this magnetic field and then somehow transverting it back to current. And so maybe I can also show this because it's not that big on the picture. There is some switch here where you can, it's not focusing, where you can switch off this probe, and you can see that you can set it to 100 millivolts per ampere or 10 millivolts per ampere. And so we will switch it to this, and so at the end, of course, we will measure at some oscilloscope the voltage, and then by this factor we can convert the measured voltage, it's not focusing, anyhow, you have seen it, to a current. Okay, and I also have in this box brought a high voltage probe. Why do you think it's a good idea to have a high voltage probe to measure voltages at this not really high voltage motor? We can come back to this in a second. What I've also here brought with me is some picoscope. I think you also have some of those at your university to do experiments. At least is what I've been told or maybe you are planning to buy some, something like this. So this is a nice oscilloscope that you connect to your computer via USB. They are not super expensive, so this is a very simple one that is just 150 euros. It's not super high in bandwidth, just 10 megahertz, but this is totally sufficient to do these kinds of measurements, and you get a nice software to do these measurements. And so it's rather cheap, and for this, quite powerful. And if I zoom into the picture, then you can see here that the maximum input voltage is 20 plus minus 20 volt peak. So if you exceed the 20 volts, you might destroy the scope. And of course, I don't want to destroy this. So, but the motor, as I've mentioned, the motor is built for 12 volts. Why should I exceed the 12 volts voltage? Yeah, exactly. So if we switch on the motor, then the motor is running and there's some energy stored in the mechanical inertia of the motor, and there's also energy stored in the coil, in the inductance of the coil. And if we switch off the motor, the inductance, right, if we go back to the equation that we had at the very beginning somewhere, this one here, right, so if we want to stop the current, if we switch off the current, more or less instantaneously, if we have a very rapid change of current, there might be some very high voltage induced. And this might destroy the scope. And so these voltages, we have tried before, can be up to 200, 300 volts. Of course, just for a very short amount of time, but this might destroy my nice oscilloscope. And I don't want to have this, so I'm using this high voltage probe. And this high voltage probe at the end is just me go back to this picture. You can see it's a 1 to 1,000. So if I'm measuring 300 volts, then the scope will only see 3 volts. No, it will only see 0.3 volts. Yeah, it's dividing by 1,000. So it can measure up to 6,000 volts or so. This voltage we will never reach, but it's safe and we see something and it's nice. And another nice thing that I don't really need today for my measurements here, but that is nice about the scope that I would maybe like to mention if someone, I don't receive any money from this company, unfortunately, but if you buy such a scope, or if the university buys some for you to do experiments, this AWG, anyone has an idea what this abbreviation stands for? It's an arbitrary waveform generator. So it's a signal generator that is built inside the scope. And you can use the signal generator to generate sinusoidal voltages or like a square pulse function, and then use it to power your circuit. And for example, with this, it's very nice and easy to measure filters, because you can generate the input of your filter, and with one channel you can measure the input voltage, with one channel you can measure the output voltage, and then you can get the transfer function of the filter as a function of frequency by magnitude and phase, which is very nice, of course, if you do power electronics and if you need to have filters to get rid of your disturbances, for example, in terms of EMC. Okay, so this is a summary of all the instruments. Now this should be the right link. So, so if you scan this, you should come to the survey from the beginning, because there probably I forgot to insert the correct link, but this should be the right one. And so if you go to the questions there, it should once again ask you on a scale of artificial intelligence, how are you feeling today? Just click something, and then you should come to the second question, and the second question is, what measurements now? Yeah, right, I have a multimeter, I have the scope, I have a current probe, I have a voltage probe. What measurements could I do with my motor to determine these parameters? So we want to have the resistance of the motor, we want to have the inductance of the motor, we want to have this friction constant of the motor, we want to have the inertia of the motor, and we want to have this K factor that gives a relation between current and torque, or between rotational speed and the electromotive counter force voltage. So what ideas do you have to do this? And so while you are still typing, I will go back to my first slide. Okay, so yeah, I've changed the link here, but I've not changed the QR code. Oops. So no. Okay. So there we have the result once again. Very nice. So the 9 still wins. And we have a couple of answers already here. So which measurements could be done? Okay, of course we could measure something with current and voltage, because if I have a current probe, if I have a voltage probe, I can measure current and voltage. And we can directly try to measure resistance with my multimeter here, but from a current and voltage measurement, for example, how can I try to determine the inductance? There would be one way to do it with a special instrument that I've not brought today, some RLC meter. It's like a multimeter that allows you to measure not only resistance but capacitance and inductance directly, but I would also say that it's not super reliable to do so. Okay, so speed and angular speed, I'm also not really able to measure angular speed because I don't have the proper tool to do this. We could just count rotations if we like. Okay. So I will give you some more time. I think what we can do and what we can start with is, go through my slides, go back to measurements. So we've just discussed this. So what I could do is measure DC resistance with the multimeter. So let's switch over to the camera. I already have lots of cables and stuff here, but here's my motor. And here's my multimeter. And if I switch it on and switch it to the range where I can measure resistance, now you can see it's saying something like OL for overload because nothing is connected to the cables. If I put the measurement cables closely together, there must be lots of disturbances in this room because it's not measuring really a constant value, which is kind of strange, but okay. We get some result. And if I connect this to the motor, you think it's about due to the light? No. Maybe the battery is also a bit empty on the oscilloscope, but anyhow, if we connect it to the motor, we get something that does not look too bad, something like 2.4, 2.5, 2.6 sometimes ohms for the resistance of the motor. Okay. Does not look too bad. I mean, by the way, I brought all this equipment, as mentioned, in this suitcase on the airplane, and I was a bit afraid that I dropped the luggage at the airport in this bag, and they scan it, they see all the electronics, and they will directly detonate it. And so that's why I have written like a package list what is inside this, and I put it on top of the suitcase. And when I got it back from the security scan, or everything was exactly in the same order as I've packed it. So I think they did not really unpack my box, which is very good. So it worked. My plan worked with this package list. Okay, so let me quickly go back if we have more ideas. Okay, not really. So then, okay, let's maybe come back to the idea that we measure resistance, and so I don't need a multimeter anymore. So now I'm using the cables from the power supply. So they are plugged in here into the power supply. The old saying, red is black and plus is minus. No, the red is the plus, the black is the minus. And I have two terminals here, and I can also connect them to the motor. And so there's my motor. Cables are connected. Now if I switch this on, and if I use a very low voltage at the beginning, just 1 volt, then you can see here we have 1 volt, and the second reading is the current in ampere. So if we would calculate the resistance, voltage divided by current, what would we get approximately? Who's good in doing calculations in the head? Yeah, something like 1.2, maybe 1.3 ohms, right? A little less, or by a factor of 2 less than what I've measured with the multimeter. Okay. So if we increase to 2 volts, still nothing happens with the motor. We also approximately increase the current. So once again, if I divide voltage by current, we get something like the same 1.2 that we had before. Okay, And so if I go higher with the voltage, now you can see my motor is starting to rotate. And if I'm, maybe I have a, just for the recording, have a second microphone. So you can hear it. I can also, if I'm good, I could play some music with this. Okay, but you can see that we need to have a certain minimum voltage to make the motor rotate, and if we are below a threshold, then there's too much friction inside the motor so that it will rotate. Okay, so we have not really noted down values for this. We can do this in a second, measuring DC resistance with the power supply. Another thing, let's see if we have more ideas on this page. But okay, of course, you all said let's measure current and voltage. So what we could do is really measure a current voltage characteristic curve. A little bit like I did already, and take values for this. And I prepared a table. I don't know if someone has something like a larger tablet where you would be able to scan this. I just need one person now. Maybe with a tablet, because can you try it? You should come to some web page that has a table, and then you can support me and fill in values inside this table. Does it work?
Maybe.
Wait. The projector. The projector is playing tricks on us. Now it should work, maybe.
It asks me for, I guess, a name.
Yeah, just type in some name. Okay. Okay, and if I click on this link, or I think I've already opened it up here. Okay, so now you should be on this very same page. And I've prepared an empty table that says we have here the voltage in volt and the current in ampere, right? And so I can have the picture here, and I will try to do the first one. So if we have 1 volt, we have, because I need to try if I need to have comma. By the way, do you use in Spain a comma or a dot as a decimal separator? A comma. Okay. Like in Germany? Okay, so this should work. With a comma, it should work. And we can just say we will go up to 12 volts or so. I don't think we need the lamp. Well, we will just leave it. Okay, so I will turn the knob on the instrument, and you insert the current inside this table. Okay, so if we go up to 2 volts, we get 1.841. Okay, and you need to use a comma, I think, or because now it's and don't fiddle around with my table. Someone has now deleted something. Okay, can you type in once again 1.85, let's say, or one comma? Sorry, comma. You need to use a comma. I will. If I'm speaking English, I always say dot, but I mean a comma. Does it work?
Usually we say point.
You say point, okay.
In English.
Yeah, 1.8. Okay, excellent. So then we will continue with 3. And now we can see that now also the motor starts to rotate. And now interestingly, we get less current. we only get 1 point. It changes all the time, 1.3 something maybe. So anyone an idea why we get less current now?
The miniature force.
Yeah, because of this counter electromotive force. Now the motor is rotating, that's why we get this counter electromotive force, and this will be some voltage that is against the source voltage, and so it will lower this. Okay, Alejandro is nicely helping me here, which is good. So we can go to 5 volts. Yeah, and I can have a microphone here that you can hear the noise of the motor. So we can go to 6 volts. Okay. Okay, I think it just needs some time for me here to update. Okay, so now we have 7 volts and we will go up to 12. So I think we don't need to have these remaining numbers here. And maybe I can try to make this then a little larger, but I don't want to waste too much time. So now we have 8 volts. And now you can see that the current is increasing all the time once again. So, so I will go up to 9. And then we lost some value in between, right? But no problem. We will go back to this later on. So then we have 10. And now, interestingly, we get, I think these current values are changing a bit. We will see later on why this is the case. And I will go up to 11, and then I will go back to 6, and then we have done this measure. So now we have 1.8 something once again. And I will go up to 12. And then we have going at 1.8. 3, but it changes. Okay, and I will go back to 6. And for the 6 we have now much less. Okay, but we get some curve. Okay, so I will switch it off. And thank you, Alejandro. Excellent. So now what we could do very quickly, I can maybe try to zoom in a bit to make the values appear a little larger. And one nice and easy thing here is, of course, that we could now insert a diagram. And we want to have a line with points connected to each other. And yeah, usually okay. Okay, this is looking better. Still not very good, but anyhow, okay. So, so what we can see is at the beginning, and maybe I should add some 0 and 0 at the beginning. Can I move this all down? I know. I won't fill it around too much. But at the beginning, we have quite a high current, and then the current more or less stays constant, and we have a very small increase over voltage. Yeah, and so this value here is a bit off that we deleted in between. We should more or less get a linear curve there. It's not looking that good, but okay, we will stick with this. Okay, thanks anyhow. So then to now measure the inductance, we really need to use the scope and measure time-dependent behavior. And so we can start with the blocked motor. And for this, I think I need to rotate it once again and make the speed a little slower because I've drilled a hole somewhere in there. So now you can see that I perfectly matched this because I have a screw here. And with the screw, I can block the motor so that the motor won't rotate anymore, right? So now it's blocked. Can't do anything anymore. And so I could also go up for higher currents or for higher voltage. And oops, now we have already more than 5 ampere. And I will switch it off once again because now there is no counter electromotive force and we just have very high currents and the thing will just heat up very quickly. Okay, so then I can use my scope here. And at the scope, instead of this high voltage probe, connect my current clamp. And you can see that the current clamp, it's very difficult to see because it's black on black. There's an arrow pointing in this direction. So if I want to measure positive current, it should go in this direction. And that's why positive current we have on the red terminal. That's why I will connect the current probe like this, that I'm measuring positive current in this direction. And maybe I would like to have a real switch to switch the motor on and off. So I have another cable. Everything is a bit improvised, but it worked quite nice. So I have another cable and I have a small switch that I can switch on and off. So I will connect it to the switch and connect it to here. And just a quick check. So if I turn on the power supply, nothing really happens because the switch is turned off. And if I turn on the switch, now you can see that we get a high current. And if I switch off, current is gone. Okay, and so now we can move over to my oscilloscope software, which is somewhere here. And this is the trial measurement that we did in the preparation. So now at first I will switch to the current probe. And I need to turn on the current probe to the setting. And we can just maybe have no trigger and just leave it running. So no trigger at all and play. Okay, now we can see, okay, now we get some readings from this current probe. And the current probe always depends a little bit on how you orient it because it will also measure the DC magnetic field, like a compass. So in whatever direction I have it, I need to, there's some knob to null the field. Okay, this is looking quite nice. And now we are expecting to have something like plus minus 5 ampere. So I will go to this setting and as you can see, if I switch on, we get a current. If I switch off, current is gone. If I switch on, we have a current. If I switch off, current is gone. Now I want to see in the software exactly the moment, or with the scope exactly the moment when I switch on. How do I get this exact moment when switching on the current? What function do you use at some oscilloscope to capture a certain moment in time? Have you done oscilloscope measurements? And what setting or which button do you need to push to get a steady picture? If you are measuring, let's say, some sinusoidal function or some rectangular pulse train, usually sometimes the sinusoidal would be here and there and it would be always jittering around and you won't get a clear picture. What setting do you need to use that so that always at the same time when the function repeats itself that it's always starting at the very same position? A trigger, exactly. So let's use a trigger here. Unfortunately, this is somehow hidden here on the projector. So, but I can set a trigger, and I will set it to single, and I will set it to a rising edge, and I will set it to maybe something like 1 ampere of current. And then you can see here this dot, this is the trigger point. And so now if I switch on, we get a nice function. I will make the time range a bit smaller, trigger once again, switch on, maybe make the time range once again smaller, trigger again, and oh, this was switching off, this is switching on. And then you can see, okay, my switch is not perfect. Yeah, sometimes the mechanical contact is flipping a bit. But this looks quite nice. So I will leave it with this, maybe do a, oops, maybe, don't do something wrong. Maybe do a screenshot. Okay, so this is the current when switching on the blocked motor. What type of function do you see there? And how could we from this somehow calculate the inductance? Have you seen such a function before?
It's like when a capacitor charges.
It's exactly. It's the same thing as if you would charge a capacitor over a resistor at some constant voltage source, and also if you would look at the charge on the capacitor or the voltage on the capacitor, you would get exactly the same curve. And it's some exponential function, and you get like exponential charging. And it's the same here. So we have a constant voltage, we have a resistor, and we charge the inductor, and we look at the current. And so from this slope here, we can determine a time constant, and from this time constant, we can get the inductance. And so the time constant, I've set it to 2 millivolts per division. So what we would need to do is, from this point where it starts, draw a line that touches this line here and check where the line then touches the constant value. And yeah, we would get something like maybe half of this time division here, maybe 1 millisecond, something like this, right? Okay, so remember this. So what else could we do? We could, and I maybe need to rotate the motor a bit in the opposite direction to remove the screw once again. So I will just reverse the terminus and switch it on for a very short time. But maybe with less voltage, because otherwise it will be directly blocked once again. So this is now switched on. If I switch it on and off very quickly, okay. So now it's unblocked. Now I can remove the screw once again. And now we could repeat the same experiment with the motor that can rotate. And I've checked if we go to 12 volts, it's a bit much. But if we go to 10 volts, it's working nicely. So once again, I can switch on and off, right? And so now if I trigger the measurement once again, and if I switch on, okay, we get way too much. Way too much current. Okay, this looks good. And then maybe go back to 10, and then we need to have a bit more of time scale and run it once again. Okay, this is not looking too bad. Maybe one time scale back. Okay. And so this is what we get if we switch on the idling motor. So you can see that there's also a very high inrush current at the beginning. That is here almost something like 10 ampere. And then, yeah, why do we get this high current at the beginning? I will do a screenshot, and I will maybe just repeat it once again to see if it's, yeah, so if I switch it on again, curve changes a bit, but we get more or less the same thing as before. I could, I think, also go to repeat. No, and trigger once again, and then I could have many repetitions of this, and then you can see that I get more or less almost the same curve. So why do we get such high current at the beginning? Because of the inertia, exactly. Because this is now the mechanical inertia of the motor. So if we switch on, we just have the resistance and the inductance of the electrical part, but the inductance of the electrical part is very small. So the current can increase very rapidly, and the motor needs some time to start to rotate. And the more speed we have, the more electromotive counterforce we get. And so that's why then the current will go down. And then we reach some steady state current. And the steady state current is not really a constant current. There's some ripple on there. Why do we get this ripple? Why is the current not really staying constant, but why is the current moving up and down? Now we would need to know how this motor works on the inside. So what is inside such a DC motor that might make the current go up and down all the time? How does the, say again? Yeah, because of the brushes, right? The current needs to go from the outside to the rotor on the inside, and there are brushes, and these brushes are moving, and they make that the current will go up and down all the time. So what we see here is the influence of the brushes, and from this we could also determine the rotational speed of the motor if we know how many brushes there are and so on. Okay, I just have shown you this curve because yeah, this is what happens if we switch on this idling motor. Still, I would say it's difficult to determine the inertia of this motor from this. We could somehow try, but the problem is that it's a very, if I would ask you what type of function is this? By the way, this reminds, okay, here. But what type of function is this? No one knows. Difficult to say, right? It's a combination of exponential charging, and then we have this counter electromotive force, and it's going down again, and it's difficult to say what type of function this is. And from this type of function, it's not that we can define a time constant and do stuff like this. Okay, so this is a nice measurement, but it's not really helping us in determining the parameters of the motor. So what I will do now is, instead of my current clamp here, current probe, I will connect this high voltage probe to the same channel as before. And this high voltage probe has two connectors. So this is like the ground, this is like a reference, and the red one is like the probe where I can measure voltage. And so now I will be trying to measure voltage, the voltage across the motor. So the motor terminals are here. The blue thing is the minus terminal. So this is where I will connect the ground of the probe. And then this here is the plus terminal. This is where I will connect the probe itself. And there's a small hook that should just hook in there. Okay, so this is looking nice. Once again, if I operate the switch, motor is starting to rotate and I can start and stop the motor, right? Okay, so now I will change the probe here and we'll go from my current clamp to this 1 in 1,000 high voltage probe. And now it can measure up to 1 kilovolt. This is of course way, way, way too much. We want to do something like maybe plus minus 50, which is good. And I can just have it running all the time. And now nothing happens, 0 volts. If I switch on, okay, you can see we go up to 10 volts. I can maybe go up to 12 and switch off. Switch on, switch off, switch on, switch off. Once again, if we want to see the switching off, we need to have a trigger. So I will go to a single trigger and now I will change, you cannot see it, I will trigger to the falling edge. And maybe to this position. No, maybe a bit below. At minus 10 volt. Okay, so now we can run it. I switch on, nothing happens. If I switch off, it should trigger. Oh, it doesn't. Too sad. Maybe I should go to positive voltage. Okay. So now it's triggered. Switching on. Okay, there's a transient for switching on. Now I will trigger again. Okay, and there we see the switching off behavior. So what can someone explain? I will try to zoom in a bit. So here we have 12 volts. Here we have 0 volts. And in between the speed, no, the voltage that I measure at the motor is going down, is decreasing. And the voltage, yeah, why do I, but I've switched off the source. Why do I still measure a voltage at this motor? Yeah, because of, this is, at the end, this is this electromotive counterforce. This is the voltage that is induced by the motor itself in the moment where the motor is not acting really as a motor, but more as a generator. There's the inertia of the motor that keeps the motor turning, and like a generator, you turn it, you get some voltage. And so this is the voltage that is self-induced by the electromotive counterforce of the motor. And what we said is that this voltage is directly proportional to the speed. So what I see here is the speed of the motor, how it's going down. And as you can see, it takes something like 140 milliseconds for the motor to stop because of the friction inside the motor. If we would have less friction and more inertia, it would take longer. If we have, and so on, right? If we have less inertia, more friction, the motor would stop even faster. So from this type of measurement, here, this is now a very nice function because it's more or less just a straight line, just a linear function. And we can once again have a time constant, which is 140 milliseconds. And from this time constant, determine the mechanical inertia of the motor. A much nicer curve than the curve that we have seen before, because this is just linear. Okay, something interesting anyhow, or nevertheless, is happening here in this time period. And so I will try to zoom in there a little bit and maybe, so let's see if the triggering works, right? So if now I'm triggering all the time. So if now we have from 20 milliseconds went down to 2 milliseconds per division. And you can see that there's a real strong voltage spike there. And if I go down even more, maybe to 200 microseconds, you can see that my switch is not working that nice. I will maybe go back to the initial zoom. Okay, but this is a quite nice picture. So we have the 12 volts of the motor. Here my switch is already trying to switch a little bit, but nothing really happens. And then we get, for a short time, kind of a constant voltage. And then we get this voltage spike, and then the voltage is going up again, and we get this very, in comparison with this, very slow linear decrease of the voltage. So does anyone has an idea what is happening here?
Maybe the brushes changing the path.
Yeah, so it has something to do with the brushes at the motor, but yeah, maybe not. I would guess that this is way too fast to see any movement of the brushes, because we are now in a microsecond range. And I mean, the motor is not rotating that fast, so that even for 100 microseconds, I would guess that the position of the brushes stays more or less constant. So I can try to zoom in a bit more. Okay, I'm not really getting that. This is now once again looking quite nice, right? So we are switching. So this is what is happening here is, if I switch off, as you said, there is the inertia of the motor, but there's also just the inductance of the motor. And the inductance of the motor would like to push the current. And if I switch off with the switch, I mean, there are two mechanical contacts that open up. There can be no current anymore. Yes, there can be a current, because there will be some, like a small arc. There will be like a very small lightning inside the switch. The air will heat up and turn into a plasma and will burn away the energy that is stored in the inductance. So at this time where we have this constant voltage, there's like an arc in the switch. And then we get this voltage transient when the arc stops to burn. Then still some very high voltage is induced. And if now it's plus minus 50 volt, I will go up to plus minus 500 maybe and switch once again. And so now you can see that we reach, unfortunately the numbers are not visible here. Maybe I can move this a bit. Yeah, so now you can see that we easily reach something like minus 250, minus 300 volts. That's what I mentioned at the beginning. I don't want to destroy my nice oscilloscope. That's why I'm using this high voltage probe. Okay, so excellent. So now we have done lots of measurements, switching on the block motor, switching on the running motor, and the voltage transient when switching off the running motor. So now we can quickly go back to the model and see what we can do with this. So if we have the blocked motor, if the motor is not rotating, there is no speed. If there's no speed, there will be no electromotive counterforce. So the source is not there. And if it's the static behavior, if the current does not change, then also the inductance does not really matter. So from this static observation of the block motor, we can easily get the resistance. And we could go back to our table here. And from the values inside this table, here, this was where the motor was not rotating. We could easily calculate the resistance. Okay. So then we could take a look at the static behavior of the rotating motor, of the idling motor, of the running motor. Once again, if it's static, if currents are in a steady state and do not change, we don't need to take into account the inductance here and there. So Still we have a current that will create a torque, still we have a speed that will create this back electromotive force. So we can write down some equations and reformulate these equations a bit, and from this we get the electromotive counterforce, and we can also get the resistance that takes care of the friction. Right, so from the values that Alejandro helped me in putting up this table, from values here we have a voltage and current on the electrical side, and we already have determined the resistance from the first two rows, so we can put them into this equation and calculate this K constant and calculate the friction constant. Now we have already 3 parameters of our motor, right? So now we only need the inductances, and the inductances we get from the dynamic behavior. And we can do the dynamic observation of the blocked motor. Once again, if the motor is blocked, what I've done with the screw, then we don't have any speed, any rotation speed, we don't have any counter electromotive force. So yeah, we get this voltage law, which is a differential equation. We could solve this differential equation or measure this time constant, and from the time constant determine the inductance of the motor. And the time constant, if you remember that we measured, was something like a microsecond. We have the motor resistance already, then we can calculate the inductance of the motor. And I mean, it's very easy. The motor resistance was something like, what value did we measure approximately? Or if we go back to the table here, what value for the resistance do we get here? I mean, I can also do the calculation here. Resistance is voltage divided by current, and we get 1.2 approximately, or yeah, something like 1 ohm. So if this is 1 ohm, this was 1 millisecond, then we should get something like 1 microhenry for the inductance of this motor. 1 millihenry, right? Ohm times millisecond is millihenry. Okay, and then we can do dynamic observation of the running motor. So we already know this, we already know this, we already know the K factors here. The only thing that we don't know is the mechanical inertia. And then we did this hard switching off. So if the motor current is 0, we have no torque anymore. So the mechanical part here simplifies a lot. And once again, we can have a time constant. And from this friction resistance that we have not really calculated yet, we can also get the mechanical inertia of the motor. So not too complicated measurements, not too complicated model, and not too complicated formulas to get all the parameters of the model. That's more or less it. And so, yeah, on Friday then, we will have the second part of this session. We will do some simulation with LT-SPICE, and maybe what we can, and don't use this link here. This is again the wrong one. Just go back to the one that you had before, and probably you have all filled the last question, right? I know. Excellent. So we don't have more answers here. We can check if there are any questions, but there are no questions. So we can come to the third question. How much experience do you have with electric circuit simulation in LT-SPICE? And I don't know. The zoom here is very stupid. You cannot make the letters larger. But the first option is I've never heard of LT-SPICE before. This is what most people have said. Some about the fifth, so this is about a half of the people, about a fifth of the people said, I've heard that LT-SPICE exists, but I've never used it. And about another fifth said, okay, I've used it once, and some people have used it a couple of times, and no one said he or she has a huge experience. Okay, excellent. So this is then what we will do on Friday. Do some introduction into LT-SPICE. And for this, we will meet in a computer lab. Do we already know which room this is?
Yes, C2.4.
C2.4. wherever this is, I will find it. And yeah, hopefully LT-Spice there is already installed on the computers. I mean, anyhow, if you want to bring your own computer, which I would also maybe encourage you to do, you can download this from this website if you just Google for or search for linear technology or no LT-Spice and download, you will find this. I mean, this LT-Spice is called LT-Spice because it once was given out by a company called Linear Technology. That's why the LT-Spice. But a couple of years ago, Linear Technology was bought by Analog Devices, and they were clever enough to not rename the software into AD-Spice or something like this. It's still called LT-Spice, but now you can download it on the website of Analog Devices. And it runs under all modern operating systems, and it's not that big. So if you download it, it should be just a couple of 10 megabytes. And the nice thing is it's freeware. You don't need to have a license for this. We also shortly discussed this in the morning. So even for commercial purposes, you can use this free of charge, which is quite nice. And that's why, especially in Germany, it's also used by many companies. So this, the manufacturer of my nice motor here also uses this software, LT-Spice for simulations there. But unfortunately, it's closed source. You cannot look into the software that really happens there, which is sometimes bad for research. I mean, you cannot really check what calculations are done there. And the maintainer is Mike Engelhardt. He's still quite active. Unfortunately, I've never met him in person. He's always wearing various types of hats. This abbreviation of the program SPICE is like an acronym, like LASER. Does anyone know what LASER stands for? It's light amplification by stimulated emission of radiation, right? This is what LASER stands for. And SPICE is also some kind of acronym or backronym. It's simulation program with integrated circuit emphasis. So some simulation program for circuits and so on. And SPICE, of course, in English also means spice. And that's why they are sometimes making fun of this and saying, okay, cooking with LT-Spice with Master Chef Mike Engelhardt. Yeah, and okay, the remaining stuff about the simulation, I think we will discuss on Friday. So I will quickly jump over to the last slide of my presentation, which is this here. So thanks for your attention. And yeah, I don't know if you have more questions. And then I don't need to forget, I would also do the obligatory selfie. So if you don't want to be there, just but my camera is not that good. And maybe I will take one more. Okay, excellent.
Matthias, do you recommend LT-Spice for lessons?
I would recommend LT-Spice for many simulations. So it's from my point of view, a very good and very nice program. It's, from my point of view, quite easy to get into this program. And it's not that big. It does not consume too much space on your computer and so on. And still you can do a lot with it in electrical engineering. So from simple circuits to complicated circuits, you can also model power electronic circuits. You can also model filters. You can model circuits that you somehow calculated in your Fundamentals of Electrical Engineering lecture. And I mean, what I've more or less shown today is that you can also model motors, and you can even model the mechanical behavior of a motor in an electrical circuit. And okay, for super special applications, there might be better programs. So if you specialize on power electronics, there might be better programs that have better MOSFET models, better IGBT models that simulate if you have very complicated inverters with special control strategies and so on. Then there might be more sophisticated programs to do this, but then you also need to have a license. They will consume more space on your computer. You need more time to introduce yourself to the program and so on. And I mean, maybe I will show this slide. This is the problem of every simulation that you do somewhere. You always have this garbage in, garbage out principle. Yeah? You can have the best simulation software if you do not use it properly. At the end, it's just a tool. And if you don't have the competence to use the tool properly, the tool won't help you. The computer will, in most cases, be always right. You need to tell and explain the computer your problem correctly, and then it will do something, and then you also need to interpret the result correctly. And yeah, then the problem is often sitting in front of the computer, I would say. Yeah, but LT-Spice, I mean, we will see it on Friday. From my point of view, it's a quite nice program. Okay, then thank you.
Thank you.
Thank you very much.